Good morning, all of you. Welcome to Sri Jayendra Rank Zone. Now we are into the second lecture of P block elements. First lecture we are already done. That is introduction and some trends, periodic trends in physical properties as well as chemical properties. Now we are continuing with 13 group elements, chemical properties in this lecture. So please make a note of each and every point where we are stressing in the lecture. That is very useful for competitive exams. Now we'll start. P block elements continuation. So chemical properties of group 13 elements. First we have done reactivity towards air. So how these elements combine with air. So all the 13 group elements react at high temperature forming trioxides when they combine with air. These elements react with air to form corresponding oxides of type M2O3 or E2O3. Both are same. So even you can take M2O3 or E2O3. Only at high temperature they form respective nitrates of type En. So all the group 13 elements react at high temperature forming trioxides first. Crystalline boron is chemically inert to air. All the group 13 elements react at high temperature forming trioxides. So here I am writing the statement again. All the group 13 elements combines with air at high temperature, combines with air at high temperature. Very important point is at very high temperature only. Normal temperature they not combine to form oxides of type E2O3. So boron is unreactive in the crystalline form. However, finely divided amorphous boron. If you take amorphous boron, crystalline boron is not reactive, but if you take amorphous boron, that's why I said all amorphous boron at very high temperature, that is 973 kelvin, it forms boron trioxide, changes to B2O3 on reaction with air plus air forms B2O3. The thermodynamic aluminum should react with air, but it is stable due to, so this way happens only. Aluminum will form. So remaining all elements will form. All other elements will form. That is second group and 13th group elements in solid form. They combine with oxygen and nitrogen in air and forms En and E2O3. For example, aluminium, 2 moles of aluminium, 4 moles of actually aluminium, combines with 3 moles of oxygen to form Al2O3. Actually, this is 2 moles of aluminium only. So 2Al. So 2Al, I'm writing it again, I'm writing it clearly. So 2Al, 2 moles of aluminum combines 3 moles of oxygen to form Al2O3. Similarly, gallium, indium, thallium also will form E2O3. So all the group 13 elements combines with air at very high temperatures to form oxides of type E2O3. So this is the example. And at very high temperature, they form respective nitrates of type En also, boron nitrate Bn, aluminum nitrate Aln, and so on. So they can combine with nitrogen also from air and forms nitrides. So boron nitride, aluminium, and very high temperature. So nitrogen with the dinitrogen, they combine with each aluminum and boron form corresponding nitrates, while gallium and indium do not react. Very, very important. Gallium and indium do not form. Gallium and indium do not react with nitrides, with nitrogen. Do not react with the nitrogen. So please make a note of this. So gallium and indium do not react with nitrogen, whereas boron and aluminium will form boron nitrate and aluminum nitrate at a very high temperature. So these are the reactivities towards air. So 13 group elements combines with air to form corresponding oxides of type E2O3, and at very high temperature they form respective nitrates except gallium indium. They form their respective nitrites, that is of type En. En means boron nitrate, aluminum nitrate, thallium nitrate, and so on. So crystalline boron is chemically inert to air. So that's why amorphous boron, powdered boron should be taken. That is amorphous boron plus air will form B2O3. So these are the reactions involving of 13 group elements with respect to air. I hope it is clear. Next, continuation. Reactivity towards air continues. All these oxides show a decreasing acidic nature. Decreasing acidic nature from boron to thallium. B2O3 is acidic. Aluminum oxide and gallium oxide are amphoteric. Very, very important. Oxide of aluminum and gallium are amphoteric, whereas boron trioxide, that is B2O3, is acidic. Rest of the oxides are basic in nature because of their highly metallic character. So B2O3 combines sodium hydroxide and forms sodium metaboate plus water. Aluminum oxide combines sulfuric acid and forms aluminum sulfate and water. Aluminum oxide combines sodium carbonate and forms sodium metaluminate and carbon dioxide. So they combine with acid and base. So that is why aluminum oxide and gallium oxide are amphoteric, whereas B2O3 is acidic because it is non-metallic oxide. These two are metallic oxides, but they are less metallic. So that's why they are called as amphoteric oxides. Amphoteric oxide means they can combine with acid and base to form compounds. Though aluminum oxide can combine with acid as well as they combine with base also. So with the base it forms aluminum hydroxide, with acid it forms aluminum sulfate. Gallium also the same way. So aluminum oxide and gallium oxides are amphoteric and rest of the oxides are basic in nature. That is indium oxide and thallium oxide are basic. Indium oxide and thallium oxide are basic, and aluminum oxide and gallium oxide are amphoteric and B2O3 is acidic. So these are the nature of oxides of 13 group elements. So these oxides when combined with sodium hydroxide form sodium metaboate. So that is sodium metaboate, and aluminum oxide when combined with sulfuric acid forms aluminum sulfate. Aluminum oxide when combined with sodium carbonate forms sodium metaluminate and carbon dioxide. So this is the reactivity towards air. Very, very important. Next continuation. Reactivity towards with acids and alkalis. Boron does not react with acid and alkalis only. First point. Boron does not directly combine with acids and alkalis. Acid means like nitric acid, sulfuric acid, etc. And alkalis means soluble bases, that is potassium hydroxide, sodium hydroxide, etc. However, at very high temperature, it reacts with strong oxidizing agents such as mixture of hot constant nitric acid. So, at very high temperature, at very high temperature, at very high temperature, boron combines with a mixture of strong oxidizing agents like constant nitric acid and concentrated sulfuric acid. So it should combine with the mixture only and forms boic acid, that is H3BO3 plus 3 moles of nitrogen gas. So boron combines with acids only at very high temperature, and that too it is not combining directly with one acid. It is combined with a mixture of hot concentrated sulfuric acid and nitric acid in the ratio of 2 is to 1. The ratio of what? 2 is to 1. Mixture of sulfuric acid and nitric acid in the ratio of 2 is to 1 to form boic acid. Similarly, boron can combine with B can combine with potassium hydroxide, that is base, at a temperature greater than 773 kelvins to form K3BO3 potassium boate plus hydrogen gas. So normal conditions boron will not form, but temperature greater than 773 kelvins boron form boates. Boron can form boates, that with sodium hydroxide forms sodium boate, with potassium hydroxide form potassium boate only at high temperature. So boron does not react with acids and alkalis. Only at very high temperature, boron combines with strong oxidizing agents like sulfuric acid and nitric acid to form boic acid and along with nitrogen dioxide. Whereas boron combines with base also at a very high temperature, that is greater than 773 kelvins, and forms potassium boate along with hydrogen gas. With sodium also it forms sodium boate, that is Na3BO3 along with hydrogen gas. So like this it takes place. With sodium carbonate, sodium bicarbonate also it forms. Next, aluminum dissolves in dilute acids and liberate hydrogen gas. In HNO3, aluminum and gallium becomes passive due to formation of protective oxide layer on the surface. Sorry. By this, what do you understand? Aluminum and gallium becomes passive. Passive means no reaction due to formation of protective oxide layer on the surface of aluminum and gallium. They are not reacting with nitric acid. Whereas aluminum can combine with other dilute acids such as HCl and H2SO4, and forms aluminum ions, chlorine ions, and hydrogen gas, lipid hydrogen gas. Aluminum also dissolved in alkali sodium hydroxide to lipid dihydrogen. So aluminum combines with sodium hydroxide and base, acid and base, and forms hydrogen gas. That's why aluminum is amphoteric in nature. Aluminum oxides are amphoteric in nature because they combine readily with acid as well as base to yield hydrogen gas. So aluminum metal, if you take on reaction with dilute HCl, it forms AlCl3 along with hydrogen gas. Aluminum also dissolves in sodium hydroxide, forms sodium metaaluminate and hydrogen gas. So these are the reactions of acid with alkalis. More reactions we'll discuss now. So at very high temperature, so boron does not react with acids and alkalis, only it reacts at very high temperatures, and that too with a mixture, concentration mixture of hot concentrated nitric acid and sulfuric acid. So concentrated sulfuric acid nitration mixture. So this is called nitration mixture. 1 mole of 2 moles of sulfuric acid, 1 mole of nitric acid, and forms boic acid along with nitrogen dioxide. So this reaction is very important. So boron combines with acids only at very high temperatures, and even with base also at a temperature greater than 773 kelvins, it forms metaborates. So potassium metaborate, sodium metaborate, and so on. So potassium borate, this is called what? Potassium borate. So these are the reactions of boron and aluminium. So let us see continuation now. Please make a note what I am writing on the slides, and even all the slides should be written. So these are the trends of reactivities of acids and alkalis. So gallium combines base. Gallium combines with base, that is sodium hydroxide, and forms sodium gallium hydroxide and hydrogen gas. So all other elements except boron combines with acids and alkalis. All other elements except boron combines with acid and alkalis. Next we have reactivity towards halogens. All the 13 group elements, all the 13 group elements react with halogen directly to form corresponding trihalides of type BMX3, where M is called metal, sorry, element of 13 group, where M is equal to boron, aluminium, gallium, indium, thallium. That is 13 group elements. So in that also thallium triiodide cannot be formed. So 2 moles of 13 group element combine with 3 moles of halogens and forms 2EX type, that is fluorine, chlorine, bromine, iodine. So you can have any examples. For example, you can write, so 2 moles of boron combined with 3 moles of chlorine gas and forms 2 moles of BCl3 solid. So this is called halides of 13 group elements. These are the halides of 13 group elements. All possible halides have been prepared for all 13 group elements except thallium, by which thallium trifluoride, thallium trichloride, and thallium tribromide have been obtained. So in thallium only, we have thallium trifluoride, comma, thallium tribromide, comma, thallium trichloride only are obtained, whereas thallium trichloride is obtained and thallium triiodide cannot be obtained. Thallium triiodide cannot be obtained because of large size. TL3 cannot be found due to large size and inert pair effect. And due to inert pair effect, TLI3 cannot be formed. Only TLI is formed. What is formed? TLI is formed. That is monohalide is formed. That is thallium iodide is formed due to inert pair effect. Due to inert pair effect. Again, I am writing, please listen. Due to inert pair effect, only thallium iodide is formed, whereas thallium triiodide does not form due to large size and inert pair effect. So thallium is plus one state is only more stable when compared to thallium plus three. But other fluorides, bromines, and chlorides will be found because they are small size. But iodine is very large size, so that's why, and inert pair effect, only thallium triiodide cannot be formed. So TLI3 cannot be formed, only TLI is formed due to inert pair effect. So these are the reactions towards halogens. So all the elements of group 13 combines halogens at high temperatures to form trihalides having the general formula MX3. General formula MX3 or EX3, both are same. So this is about reaction towards halogens, reactions towards halogens. And moreover, important point is the trihalide thallium bromide and thallium chloride is quite unstable and dissociates to form thallium bromide with plus one state plus bromine molecule, bromine gas, and even this is also thallium chloride with chlorine gas. This is also same inert pair effect. So thallium is more stable in plus one state than plus three state, and thallium will form monohalides rather than trihalides. Thallium can form trihalides only for TLF3, TRBL3, and TLCL3. And in this TLBL3 and TLCL3, that is thallium tribromide, thallium trichloride, are stable only at high temperatures. If you reduce the temperature, they are unstable and they become thallium monobromide, thallium monochloride, along with bromine gas and chlorine gas. So by this, what you can understand, thallium is more stable in plus one oxygen state only. That is due to inert pair effect. The F electrons, due to poor shielding effect of F electrons, the ns electrons are coming closer to the nucleus, and due to which what happens, the reluctance of ns electrons in bonding takes place. So reluctance means non-involvement. So in thallium we have ns to np3, so s electrons will not involved in bonding. So due to this, what happens, only p electron involved, so np1 electrons only involved. So this p electron will form only monohalides of type mx. And thallium triiodide does not form at all due to large size and inert pair effect. So these are the trends of 13 group elements of reaction towards halogens. Point number one, all the 13 group elements react with halogens directly to form corresponding trihalides except thallium. Thallium will form trihalides up to thallium trifluoride, thallium tribromide, thallium trichloride. But these are also not in this also thallium tribromide and thallium trichloride are not stable at high temperature, at low temperature, and they combine and they're changed to form thallium monobromide, thallium monochloride, along with bromine gas and chlorine gas. And thallium iodide is formed due to inert pair effect. Thallium triiodide does not form. Thallium triiodide does not form. So please make a note. This is the reactivity trends of 13 group elements towards halogens. Next, boron has anomalous behavior of boron now. Boron has very small atomic radii, hence greater nuclear attraction. Since it has very small atomic size and atomic radii, it has greater nuclear attraction on the outermost electrons. It has very high ionization energy. This gives boron distinctly non-metallic character while the rest are metals in this group. And that's why, due to this, what happens, boron has maximum covalence of 4 due to non-availability of d orbitals, while the rest have maximum covalence of 6. Boron alone exhibits allotropy, and other elements will not exhibit allotropy. So these are the anomalous properties of boron. Continuation now. And very, very important, boron shows plus 3 oxygen state only, as it does not show the inert pair effect, while others can show plus 1 and plus 3 oxygen state and does not show inert pair effect. Boron does not form cations in aqueous solutions because of its non-metal. As it is non-metal, as boron is non-metal, it will not show. What does it will not show? It will not form cations. Boron halides are monomeric. What do you mean by monomeric? They exist as single molecule, while the halides of other elements are dimeric, like Al2Cl6, whereas boron exists as BF3. So it is monomer and it is dimer. So aluminium, thallium, indium, all other halides will exist as dimer, whereas boron exists as monomer only. Boron forms a number of volatile hydrides, which are electron deficient compounds. Boron forms a number of volatile hydrides, like example B2H6, BH3, monomeric as well as dimeric. So other forms only one polymeric hydride. Polymeric means so many, like aluminum hydride. Aluminum hydride, you can see here aluminum hydride, it will form taken n times. Aluminum hydride taken n times. So this is polymeric hydride. That's why aluminum is in diagonal relationship with beryllium, because beryllium hydride also it will form BeH2 taken n times. So that's why aluminum and beryllium are diagonal relationship because their hydrates form polymeric. Polymeric means so many hydrates combined together. So many hydrates combined together. That's why other forms only polymeric hydrate, whereas boron forms only monomeric hydrate. So boron halides are monomeric. Boron forms a number of volatile hydrates which are electron deficient compounds. Other forms only polymeric hydrate. That's why they might not be electron deficient compounds because they are not existing as monomers, they are existing as dimers. Remember this, aluminum chloride does not exist as monomer, it exists as dimer. That's why it is not electron deficient compound, not an electron deficient compound because it is dimer. Only AlCl3 is electron deficient compound, but Al2Cl6 does not be an electron deficient compound. So very, very important. So this is about anomalous behavior of boron. More about this we'll discuss now. So still we have hydrates, halides also. After that only we'll discuss all these things. Next continuation. The oxide of boron B2O3 is acidic. This already we know in nature, while other similar oxides of other elements are either amphoteric or basic. For example, aluminum oxide and gallium oxide are amphoteric in nature, whereas indium oxide and thallium oxide are basic in nature. These two are basic in nature and these two are amphoteric in nature. Boron is not attacked by non-oxidizing acids. It dissolves in concentrated nitric acid forming H3BO3. As I told you, boron combines with nitric acid, combination mixture of nitric acid and concentrated sulfuric acid to form metaboric acid, that is boric acid H3BO3 along with nitrogen dioxide. Balancing you can do. So along with nitrogen dioxide. And the other elements becomes passive, especially aluminum and gallium are passive in concentrated nitric acid due to the protective layers of aluminum oxide and gallium oxide. Due to protective oxide layers of aluminum and gallium, protective oxide layers of aluminum and gallium, they are passive with the concentrated nitric acid. The other elements becomes passive, especially aluminum gallium becomes passive with concentrated nitric acid as they has due to the protective oxide layer of aluminum and gallium. Boron combines with metals to form borides, while other elements do not combine, they form alloys. So boron combines with metals and form borides. For example, here B directly combining with metal and forms metal borides. Example right here. So example B directly coming with metal magnesium boride Mg3P2. So this is called metal borides. While other elements do not combine, they form alloys. Aluminum they form alloys. Gallium it form alloys. Thallium, indium and others will form alloys. Very, very important point. The trichlorides, bromides and iodides of all these elements, trichlorides, bromides and hydrates of all these elements are covalent in nature and are hydrolyzed in water. The tetrahedral species, that is MOH4 minus, and octahedral species MH2O2 equals 6 times 3 plus, except in boron, exist in aqueous solution. The monomeric trihalides being electron deficient are strong Lewis acids. So the monomeric trihalides being electron deficient are strong Lewis acids. So there is an exceptional behavior for boron. Next, some important compounds of boron, let us see. First, we have borax, that is Na2B4 10H2O, orthoboric acid H3BO3, diboron B2H6. Diboron is very, very important, B2H6. All the three are important. Let us discuss now. First, borax. So, borax now, borax bead test also we have, very, very important. So, let us see compounds of boron. That is, first we have is an important mineral of borax. So boron has again diagonal relationship with silicon. Boron has diagonal relationship with silicon. B has diagonal relationship with silicon. That is also an anomalous property. So it is an important mineral of boron. It is a white crystalline solid and contains tetranuclear units of Na2B4O5 OH taken 4 times 8H2O. These are called tetranuclear units because it cannot form octahedral complex as its covalence is 4. So it has tetranuclear units of Na2B4O5 OH taken 4 times dot 8H2O. Borax undergoes hydrolysis. So this is Na2B4O7 dot NH2O. How does it represent as Na2B4O5 OH taken 4 times dot 8H2O. So this total is taken as Na2B4O7 dot 10H2O. This is called borax and it is being changed into Na2B4O5 OH taken 4 times dot 8H2O. So if you count the number of oxygens, it will be the same. So borax undergoes hydrolysis. On reaction with water, it forms sodium hydroxide, boic acid along with water. So this is the preparation of boic acid. Aqueous solution of borax acts as buffer because it contains weak acid and salt of strong base. Weak acid and salt of strong base, that's why it is called as acidic buffer. What is it? It is called as acidic buffer. So borax is an acidic buffer. Aqueous solution of borax acts as buffer because it contains weak acid and salt of strong base. So Na2B4O7 dot plus 7H2O forms NaBaOH taken 4 times plus H3BO4. Next continuation. Very, very important. What is borax speed test? Very, very important in the examination, entrance exam. Borax, that is Na2B4O7.10H2O, undergoes dehydration on heating to form sodium metaboate. This is NaBO2, which on further heating turns into transparent liquid solidifies to produce a glass bead, Corex borax bead. So the combination of NaBO2 plus B2O3 is called glass bead. This formation of glass bead is helpful in qualitative analysis of basic radicals. So what are basic radicals? That is metals, metallic ions. So what happens? Borax undergoes dehydration on heating to form sodium metaboate, which on further heating turns into a transparent liquid, solidifies to produce a glass bead. This is called glass bead. The combination of glass bead consisting of sodium metaboate along with B2O3. So this is called glass bead. This glass bead is useful in qualitative analysis of basic radicals. In qualitative analysis of basic radicals. So it's very, very important. That is called borax bead test. Definitely they'll ask in the entrance exam. So what is borax bead test? When borax undergoes dehydration on heating, borax undergoes dehydration on heating. So this, which on further heating turns into transparent liquid which solidifies to produce a glass bead called as borax bead. The chemical formula of borax bead is NaBO2 plus 2 moles of NaBO2 plus B2O3. So this is called glass bead, and this glass bead is employed in the qualitative test for the detection of some colored basic radicals such as copper, iron, chromium, manganese, cobalt and nickel. So these are the metals which can be identified by the use of glass bead, because these glass beads will give particular color with particular metal. So it's very, very important. And aqueous solutions behaves as buffer because it consisting of weak acid and salt with strong base. So let us see now borax speed test application. Let us see now. So the glass bead is moistened. So I'll write it in the next slide. So which type of metals can be identified? Copper, iron, chromium, manganese, cobalt, and nickel. What will happen to the glass bead? From borax we got a glass bead, which is combination of sodium metaboate, that is NaBO2 plus B2O3 boic acid. So this Sodium metabolite and B2O3 combination will get solidified and forms a glass bead. This is called glass bead, and this glass bead is used for qualitative analysis of basic radicals such as copper, iron, chromium, manganese, cobalt, and nickel. These metals can be identified using borax bead. How they are identified? Let us see now. Continuation. So metal boards exhibit characteristic color, making the bead colored. So metaborates exhibit characteristic color, making the bead color. When borax is heated in Bunsen burner flame along with chromium oxide on the loop of platinum, where a green colored CrBO2 taken thrice bead is formed, which color it is green color, which confirms chromium. So if it is forming CuBO2 taken twice, it is called blue color, which confirms copper. For iron, it is green color. For cobalt, it is blue color. And for nickel, it is brown color. So these are the colors they will exhibit. So what happens actually? This B2O3, NaBO2 plus B2O3 combines with copper sulfate. NaBO2 plus B2O3 combines with cuprous oxide and forms copper borate, COBO2 taken twice. So this glass bead combines with metallic oxide like chromium oxide and forms CrBO2 taken twice. Similarly, copper oxide, CuBO2 taken twice. Similarly, iron oxide, FeO, cobalt oxide, COO, and so on. So like this, they combine together. Nickel oxide combines B2O3 and forms nickel borate. That is nickel metaborate. This is called metaborate. Copper metaborate. Similarly, nickel oxide combines with B2O3 and forms nickel metaborate, NaBO taken twice, BO2 taken twice. This is called nickel metaborate, which is brown in color, blue, green. So that's why when borax is heated in a Bunsen burner flame along with chromium oxide on the loop of platinum wire, a green colored solution bead is formed, which confirms chromium. So that's why this metaborates exhibit characteristic color, making the bead colored. So this borax bead test is very, very important in the objective. Definitely they'll ask in the entrance exam. So when borax is heated in a Bunsen burner, the question will be like this. When borax is heated in a Bunsen burner flame along with chromium oxide or copper oxide or nickel oxide or iron oxide on a loop of platinum where what is formed. So with chromium oxide, it forms green colored solution due to the formation of CrBO2 taken thrice, that is chromium metaborate bead is formed. And with copper, it forms blue color due to the blue color solution is formed due to the formation of copper metaborate, formula is CuBO2 taken twice. With iron, it forms FeBO2 taken twice, green color. With cobalt, it forms COBO2 taken twice, blue color. With nickel, it forms NiBO2 taken twice, brown color. So due to the formation of NiBO2 taken twice, brown color is formed. So like that, they'll ask in examination. So this borax speed test completely is very important. So it is used to identify the metals such as chromium, cobalt, copper, nickel, iron. These are the metals which can be identified by using borax bead. So that is called glass-like bead. And with certain metal oxides, it will give peculiar colors. So with copper metal oxide, that is copper oxide, it forms blue color. With chromium oxide, it forms green color. With the iron oxide, it forms green color due to the formation of FeBO2 taken twice. Like this we can do. So this is called borax bead test. Next continuation. Now let us see the examples. In which of the following a salt of the type KMO2 is obtained? KMO2, potassium, metal and oxide. So answer C, both B2H6 plus KOH, aluminum hydroxide, aluminum plus KOH aqueous also will form. So what happens when B2H6, that is diboron, come with potassium hydroxide? I'll just write the equation. So please make a note. More theory is there from this chapter. Definitely we'll do that. Simply first we'll do basic topic, then we'll go for depth topic. So what happens when diboron combines with potassium hydroxide? So with potassium hydroxide, it forms salt type KMO2. KMO2, that is KBrO2. KBrO2 with salt. So this is the reaction. You can see for both aluminum and boron, it will come like this. Hydrates of boron. Next question. Which of the following compounds is formed in borax speed test? Metaborate. Easily we can say it is metaborate because tetraborate, double oxide, orthoborate. No, it is only simply metaborate. Copper metaborate, chromium metaborate, nickel metaborate. What is the formula of metaborate? We can write here CuBO2 taken twice. This is called copper metaborate. Iron metaborate FeBO2 taken twice. Nickel metaborate NiBO2 taken twice. So this is called nickel metaborate, and so on. So answer is A. Next question. Aluminum chloride exists as dimer. Very important question. It exists as dimer Al2Cl6 in solid state as well as in solution of non-polar solvents such as benzene. In aqueous solution, it exists as very important question. So generally, Al2Cl6 aluminum chloride exists as dimer, that is in the form of Al2Cl6 in solid state as well as in solution of non-polar solvents such as benzene. But in polar solvent, aluminum chloride exists as how aluminum chloride exists as. So in non-polar solvent as well as in a solid state, it exists as dimer only. Whereas in aqueous solution, it exists as how the ions will be. Let us see. This question is very important. So many times it has come for competitive exams. It is nothing but AlH2 taken 6 times, 3 plus 3Cl minus. Very important bit. Please make a note. So in aqueous solution, aluminum combines with water and forms Al hexa aqua aluminum 3 plus 3Cl minus. Is very important. Very important. Please make a note. So it exists as dimer in case of benzene as well as solid state, whereas in aqueous solution it exists as AlH2O taken 6 times 3 plus 3Cl minus. Very important question. Important bit this is. Next continuation. Borax is used as cleansing agent because on dissolving in water it forms alkaline solution. Borax is used as cleansing agent because on dissolving in water, it forms alkaline solution. So what is borax Na2B4O7? When dissolved in water, it forms alkaline solution. That's why it is used as cleaning agent, cleansing agent. Next, continuation. Boic acid is used in carom boards. This already we know. That is H3BO3. Is used in carom boards for smooth gliding of pawns because H3BO3 molecules are loosely chemically bonded and hence soft. Its low density makes it fluffy. So why it can be used as carom board powders? This question is also important. It is chemically inert with the plywood. Hydrogen bonding in H3BO3 gives it a layered structure. So answer is D. In H3BO3, hydrogen bonding is present. So due to which what happens, it forms very soft layered structure. So the entire layer will be distributed on the carom board, which makes it very soft and fluffy. For smooth gliding of pawns, that is striker. So this is hydrogen bonding in H3BO3 present. So very important question. This is also why boic acid is present, is used in carom boards for smooth gliding of pawns because hydrogen bonding in boic acid gives it a layered structure so that the entire layer is spread over the entire carom board, which makes it very soft. Next, continuation. So, some other questions we'll discuss right now based on only halides and hypohalides. Next, we'll end this session and we'll start with new topic. Next, we have very important topic. I'll share it on this so that the topic we have missed out in this thing. So right now I'll share it here. Diagonal relationship. Diagonal relationship of boron and silicon. Still, so many things we have to learn about boron that we'll discuss. Now, in this lecture, I want to discuss this. So, I am discussing right now. So, it has diagonal relationship with boron and silicon. First point, both are non-metallic nature, non-metallic character, non-metallic character. So both boron and silicon are nonmetals. Both have high melting points and boiling points and ionization enthalpy and are bad conductors of electricity. Next, second point, density and electronegativity. Density and electronegativity. So coming to density and electronegativity, both have nearly equal densities. Boron is 2.35 grams per centimeter cube and silicon is also 2.34 grams per centimeter cube, almost similar. And electronegativities, boron has electronegativity values 2.0 and silicon is almost it is 1.8. So both are having similar densities and electron affinities. So this is electronegativity value, En values of boron and silicon. And this is density values of boron and silicon. Next, third point, neither boron nor silicon occurs free nature. They both occur in combined state only. Both boron and silicon occurs in combined state only. They cannot be occurred in free state at all. And both shows allotropy. Fourth point, both silicon and boron shows allotropy. Point number 5, they do not form cations. Do not form, both boron and silicon do not form cations at all because of their non-metallic in nature. And sixth point, both boron and silicon oxides are acidic. Both boron and silicon oxides, that is SiO2 and Bi2O3, are acidic in nature. Acidic in nature. So, and both will form covalent compounds. Both will form what? Covalent compounds. So these are the properties by which we can say both boron and silicon have diagonal relationship. Diagonal relationship. And both combine with metals and forms their carbides, metallic, to form borates and silicides respectively. So this is the properties of boron. So coming to anomalous properties of boron, we already discussed, and now we have discussed diagonal relationship of B and silicon, that is boron and silicon. Next, continuation. Now we'll discuss some more questions based on these concepts, so that we have to discuss questions. If questions are not discussed, everything will forget. Let us start the questions now based on first lecture, because this is the first lecture. Second lecture we are doing, so it's very important to discuss questions. Questions MCQs now. Question number 1, we'll discuss few questions from this, then we can go for next topic. First question, which of the following, which of the following is a mineral of boron? So the following is a mineral of boron. Option A, it is colemanite. Option B, it is kernite. Option C, it is boic anhydride, that is B2O3, and option D, it is borax. So as we know, answer is option D, it is borax, because the formula of borax is Na2B4OCl dot 10H2O. This boic anhydride is B2O3. It's only a compound but not a mineral. So this is question number 1. Next, question number 2. So which is not true about borax? Which is not correct about borax? Option A, this question is important. It gives entire structure. Molecular formula of borax is molecular formula of borax is molecular formula of borax is Na2B407 dot 10H2O, Na2B407 dot 10H2O, that is option 1, which is correct only. Next, option B, crystalline borax contains tetranuclear units of B4O5 OH taken 4 times 2 minus. Next, option C, it hydrolyzes to give acidic solution, to give an acidic solution. And fourth point, that is option D. Option D, it is white crystalline solid. So the right option is, you can easily say the right option by seeing all these things. The right option is, it hydrolyzes to give an acidic solution, is the correct answer for this. It is wrong statement, because it hydrolyzes to give, it will not give acidic solution, it will give basic solution. Because since borax itself is an acid, so it will give basic solution, not acidic solution. So this is question number 2. Next, question number 3. Let us discuss now. The unexpected order of acidic strength of trihalides, acidic strength of trihalides of boron can be best explained by, this point is very, very important, just now we discussed, can be best explained by first option A, it is p pi back bonding. So why this halides of boron is more acidic than other halides? Because of the reason Second option, we have hybridization. And third option, we have trigonal planar structure. Trigonal planar structure. Trigonal planar structure. And option D, none of these. None of the above. So what is the right option? It is 100% we can say. In BF3, in BCL3, we'll see P-pi back bonding. This already explained in the lecture. So due to the P-pi back bonding, the unexpected order of acidic strength of trihalides of boron can be best explained by P-pi back bonding. Only P-pi back bonding takes place only in boron, not boron halides, not in any other halides. Very, very important question. Next question number 4. Question number 4 now. Boic acid plus H3BO3 units is polymeric. Boic acid is polymeric due to. Boic acid is polymeric due to. What is boic acid formula? It is H3BO3. Is due to option A, its monobasic nature. Its monobasic nature. Option B, it is acidic nature. Its acidic nature. Option C, the presence of hydrogen bonds. The presence of hydrogen bonds. And option D, it is due to the presence of hydrogen bonds, and it is due to its geometry. Its geometry. So the right answer is, for this easily we can say, since H3BO3, boic acid means what? It is nothing but H3BO3. H3BO3 contains hydrogen bonds. Hydrogen bond. Due to the presence of hydrogen bonds, this hydrogen is linked with boron of other. This boron is linked with hydrogen of other. Like this, it forms polymeric. It is polymeric due to presence of hydrogen bonds. Very, very important question. This is also, it is polymeric due to presence of hydrogen bonds. Next question. Question number 5. Question number 5. The name and formula of the compound boron, which is called as, the name and formula of the compound. The name and formula of the compound of boron, which is called inorganic benzene. Inorganic benzene. Inorganic benzene are option A, borazole B6H6 formula they are given. You have to identify whether it is correct or wrong. Next, borazine. It is again B6N6. Next, third option, it is borazine. The name is correct, formula is wrong. Formula is correct means name will be wrong. It is B3N3H6, and option D is nothing but bosine. It is B6N3H6. H3 is given. So straight away, easily we can write the answer for this concept. We will discuss bosine. It is B3N3H6 in organic benzene, because the structure will be like this: B, N, next again B. So it's unable to draw the structure because of digital pen. We can refer the structure easily in the textbook. It is given clearly. So it is nothing but B will come like this 3 times, and between N will come, in between N will come, in between N will come. So like this benzene it will form B3N6. Next question. Question number 6. Question number 6. Which of the following molecular hydride? Which of the following? This question is also important. Which of the following molecular hydride, molecular hydride, the following molecular hydride acts as Lewis acid, acts as Lewis acid? Option A, ammonia. Option B, it is diboane. It is called as diboane. We'll call it as diboane. Option C, it is water. And option D, it is methane gas. So straight away blindly we can say boron hydrates are acting as Lewis acids, because boron compounds are acting as Lewis acids because they are electron deficient molecules. So answer is B, because they are electron deficient molecules. Electron deficient molecules. Since they are electron deficient molecules, they are called as act as Lewis acids. They are acting as Lewis acids. Next, question number 5. Question number 6 and 7, sorry. Question number 7. We'll discuss up to 10 questions in this lecture. The stability of, this question is also very, very important based on general properties. The stability of +1, the stability of +1 oxidation state, the stability of +1 oxidation state increases in the sequence, increases in the sequence, increases in the sequence. Option A, it is thallium less than indium less than gallium less than aluminium. Option B, it is indium less than thallium less than gallium less than aluminium. Option C, gallium less than indium less than aluminium less than thallium. And option D, finally, aluminium less than gallium less than indium less than thallium. So what is the stability of +1 oxygen state increases in the sequence? Solution is, since due to inert pair effect, thallium is more stable in +1 state. Thallium is more stable in +1 state, +1 state than in +3 state. So highest will be for thallium. And the answer is aluminum, gallium, indium, and thallium. Whereas aluminum, gallium, and indium are more stable in +3 state than in +1 state. So please make a note. This is very, very important. Next question number 8. So this question is very, very important. Due to inert pair effect, thallium is more stable in +1 state than in +3 state. That's why the order goes like this. Thallium is having highest. So next question number 8. Na2B4O7. Na2B4O7 dot 10H2O. This is called borax. Is correctly represented as correctly represented as option A. It is 2NaBO2, that is sodium metaboate dot NaB2O2 dot 10H2O. Second option, Na2B4O5 OH taken 4 times dot 8H2O. Option C, Na2B4H2O taken 7 times O7 outside dot 6H2O. And fourth option, all of the above. So this is answer is 100%. We can say it is represented in the form of Na2B4O5 taken OH 4 times 8H2O, because it is correctly represented as Na2B4O5 OH taken 4 times dot 8H2O. So answer is second option. Next. So these are the important questions. From more questions we'll discuss, and more about boron also we have to discuss. Definitely don't think this is the end of boron topic B. So now with this I'm ending this session. So what we have discussed so far, please follow the same, and you do more questions based on general physical properties and chemical properties, and at the end of the chapter anyway we are going to discuss all those questions. Thank you all.